With the simple harmonic forcing of undamped systems taken care of, now we can increase our complexity and see what happens when we have an underdamped system. So this will focus only on underdamped systems. We will not look at critically damped or overdamped forced systems in this course, although that can be seen in the textbook or in other sources. So in the case where we have an equation of motion in the form of mx double dot plus cx dot plus kx equals f naught cosine omega t, we'll only deal with the case where the right-hand side is cosine for right now. Similar solutions will exist when the right-hand side is a sinusoidal function. We want to find the total solution for x of t for this ordinary differential equation. So in contrast to what we looked at before, we now have a cx dot term on the left-hand side, and this damping is going to complicate our solution. The first step in getting our total solution is to find the homogeneous solution. So what happens when our left-hand side is equal to 0? Well, again, we've already solved this problem. That's what the free vibrations section was all about when we were talking about underdamped systems. So the homogeneous solution, when we had an underdamped system, had this form where we had an exponential times a cosine function. And in free vibrations, we were able to find that x term, the amplitude, and that phi term, the phase. Notice the notation here. I'm using an x naught and a phi naught for the homogeneous solution. We can't yet solve for x naught and phi naught because we can't apply our initial conditions until we have the total solution built. So the homogeneous solution we are going to put aside for now, and then at the end we are going to solve for that x naught and that phi naught. So we have to wait on that, and in the meantime we are going to look at the particular solution. And this is going to come from the form of our right-hand side and the left-hand side. So when we have a right-hand side that's just a cosine function, and we have the left-hand side now has an x double dot and an x dot and an x term, it's a little bit more complex than what we saw when we had no damping, where our particular solution just was a cosine function. Now, because we have that x dot term, it's going to be a cosine function plus a sine function. But I'm going to rewrite it instead as just a cosine function with phase, like we did in free vibrations. So again, this is coming from a particular solution that is usually written as like an a cosine plus a b sine. This is just rearranged to be an x cosine and a phi. So we have an amplitude and a phase. Notice again, this is x and phi that are attached to the particular solution, while x naught and phi naught were attached to the homogeneous solution. Without going through all the algebraic details, we can put the particular solution here into our original equation, and we're going to be able to solve for the x and the phi. And if we do that, we get this to be our x value and our phi value. So again, more complicated than what we saw previously because we have that x dot term. With now knowing the x and the phi, we can turn our attention to finding that x naught and phi naught value by applying our initial conditions. So if we have initial conditions where our initial position is x naught and our initial velocity is x naught dot, we're going to get our total solution with our x naught and phi naught values are pretty complicated now once we have damping. But if we go up here, this total solution is formed from this homogeneous part plus the particular part. And at this point, everything is already solved. We just have to put in a lot of parameters into our x naught and our phi naught to get those values. And in fact, the x naught and the phi naught use the x and the phi that we found up here above. So all of this is going to take place in that parameter step using our initial conditions to compute x, phi, and then x naught and phi naught. And then we're able to put those into our total solution. And if you notice what the total solution looks like, we have from the homogeneous part this exponential times a cosine. So we're going to have oscillations at the damped frequency from the homogeneous solution part, and we're going to have oscillations at the driving frequency from the particular part. So homogeneous part plus particular part. But what's going to happen to this x of t, the total solution, as time goes forward? Well, the homogeneous part has that decaying exponential. We have e to a negative power, and that negative power gets larger and larger as t goes to infinity. So that whole homogeneous term is going to die out. It's going to get smaller and smaller as t goes to infinity. So what we have left as t starts to get large is we're going to have just the steady state behavior. So that x steady state, and it turns out the steady state behavior is just the particular solution, since the homogeneous solution for these underdamped systems goes to 0 as time goes towards infinity. So given enough time, the entire behavior of our system is just going to be that particular solution, that amplitude x that we found and that phi that we found. And if we remember, that x and that phi, from back here, x and phi had nothing to do with our initial conditions. They just had to do with the amplitude of forcing and how our system was put together with the springs, the dampers, and the mass. So at steady state, it eventually doesn't matter what the initial conditions were. It's going to be acting just as this periodic forced system where eventually it's just oscillating at the driving frequency. And if we think back to what we looked at in system dynamics, where we were looking at systems undergoing simple harmonic forcing, we were using the Bode diagram to see how the amplitude of the system, of the output of the system, was behaving in terms of omega, and we were looking at how the phase of the system was behaving in terms of omega, because we were looking at steady state, how was our system behaving. That's identical to what we're seeing here. At steady state, just the particular solution is what matters, and we're going to see that the x and the phi are indeed dependent on what that driving frequency was. So here's the relationship that we saw mostly graphically in system dynamics. Here we're getting this exact algebraic solution for why is x affected by the driving frequency. Well, we see here because that driving frequency is in the denominator. And why is the phase affected? Because it shows up in the denominator of this term that we're taking the arctangent of. So that's where the x and the phi are coming from, why they're affected by the driving frequency. And what we said was that eventually at steady state, the system is going to be oscillating at the driving frequency, just with a different phase phi and a different output amplitude. Here, we're calling it x.